Hello student, to the course of physics of linear and nonlinear optical waveguides. So today we have lecture number 15. In the last lecture we started the concept of material dispersion. So we will going to continue with that concept. So we started with Selmer equation. We derive this equation This is the equation we derived in the last class, that how the refractive index should vary with respect to lambda. Now, today we will introduce the well known Cauchy's equation. Which is a empirical relationship between refractive index and wavelength. So, if I write n as a function of lambda, then one can have a empirical relationship in explicit form like this. This is the most general form. And A, B, C, these are the Cauchy's constant. In a few experiments, we determine this A, B, C, this Cauchy's constant, and then we know how the refractive index is varying with respect to lambda. We have the explicit form. Now, I can simplify that. Simplify to the first order, and then I can have the relationship like this. As I mentioned, A, B are constant. It is called Cauchy's constant. Well, one can directly derive the Selmer equation, this Cauchy's equation from the Selmer equation. So, we can simplify the Selmer equation as well. So, simplified Selmer equation is something like this. Taking only the first term, there is a summation sign. So, I am taking the first term in the summation, and I can write the expression in this way. So, this is the simplified Selmer equation, and now I can write this expression as 1 plus A lambda square divided by lambda square 1 minus lambda 0 square divided by lambda square minus 1. I take the lambda square common out of that and then I put it as minus 1. So, this equation is simply 1 minus lambda 0 square, it should be plus if I expand this, to the power 4 divided by 4 and so on. With the condition, this is, one can write this condition that I can do that when lambda 0 divided by lambda is very less than 1. That means, my working wavelength is far away from the resonance wavelength. In such condition, I can write in this way. Now, if I want to plot the refractive index as a function of lambda in this regime, when lambda 0 divided by lambda is very less than 1. So, that means far away from any resonance frequency or any resonance wavelength. So, in this direction I will going to plot n as a function of lambda, and this is lambda as usual. Then the curve will be something like this. This is the curve that with respect to lambda it will gradually decrease. Generally that is the form. Now, from Selmar equation, I can write n square lambda is nearly equal to 1 plus a1 plus a1 lambda 0 square divided by lambda square, taking only the lambda square term. There are many other terms like lambda to the power 4 and all these things, and you can see that this simplified expression of Selmar equation under the condition that lambda 0 divided by lambda very less than 1 can merge to the Cauchy's equation. So, it just try to correlate that the Selmar equation and the Cauchy's equation together. So, now here we neglect all the higher order terms like 1 divided by lambda to the power 4, etc. Now, from Cauchy's equation I have n as a function of lambda as a plus b by lambda square. Also, I am not going to take any higher order term, only just take the first term lambda square, and then if I want to find out what is n lambda n square, then it should be a plus b lambda square whole square, which can be approximated as a square plus 2 AB divided by lambda square. Again I neglect 1 by lambda to the power 4 term is neglected. Now, if I compare these two equations side by side, whatever the expression I have here, this is the expression I have exploiting the Selmayer's relation, and another equation I have this one exploiting the Cauchy's relation, and essentially these two things are same. So, if I compare, then I can have, say this is 1 and 2. So, from 1 and 2 we can have A square is equal to 1 plus A1, which gives me A as 1 plus A1 whole to the power half, and 2AB is equal to A lambda 0 square, because the coefficient of 1 by lambda square is A1 lambda 0 square. So, it should be A1 lambda 0 square. So, from that I can have the value of B as lambda 0 square A1 divided by 2 of A, and A already I figure out. So, this one. So, if I know the value of lambda 0 and A1, then I can correlate this lambda 0 and A1 with the Cauchy's constant A and B. So, this is a relationship between the Cauchy's constant and the constant that one can have from Selmayer equation. Well, after that, the next thing that we will do to find out the dispersion. Once more, in terms of group velocity, phase velocity, etc., how one can define dispersion, that we going to learn. So, first the wave vector. The wave vector k is essentially a function of frequency, and that is the main reason to have the dispersion. So, k should be written in this way. K is omega divided by c multiplied by n omega, where n omega is a refractive index. Now, what is phase velocity? This is Vp is equal to omega by k, and omega by k is nothing but c divided by n omega. That is the expression of the phase velocity, that we know, this is nothing new. Now, what is group velocity? This is Vg equal to d omega dk, that is by definition this is our group velocity. So, 1 by Vg inverse of group velocity is dk, which is a function of omega and d omega. It is convenient to write 1 by group velocity because we know the expression of k, explicit expression of k omega. K omega I already defined here, wave vector, it is omega divided by c, then n omega. So, this quantity is 1 divided by c n of omega plus omega dn d omega. Just make a derivative with respect to omega of whatever the k I have, and I am going to find what is my Vg. So, Vg is essentially c divided by n function of omega plus omega dn d omega. This next part is interesting. In the phase velocity we have c divided by n omega, that is true, but here for the group velocity calculation I have c divided by n omega, but additional one term is there, which is the variation that gives me the variation of n with respect to omega. That is important here, this term. Now, if I want to find out what is the expression of Vg in terms of lambda, then so in terms of wavelength, how one can write that? Because normally why I am doing that? Because n normally given as a function of wavelength, n as a function of lambda is normally given using Cauchy's law or Selmayr equation. N as a function of lambda is known. So, it is expected that Vg should be represented in terms of omega as well. How the group velocity will going to change with respect to lambda is meaningful, because n as a function of lambda is given to us. So, in order to find the value of Vg in terms of lambda, we need to use the relation of omega and lambda. Omega is 2 pi c divided by lambda, which directly give me the relation d omega d lambda as minus of 2 pi c divided by lambda square. Just make a derivative with respect to lambda. Now, dn d omega, I need to replace it as dn d lambda, and using the chain rule I can write this. So, dn d lambda d omega is simply minus of lambda square divided by 2 pi c into dn d lambda, and essentially Vg becomes c divided by, in the denominator I have n omega, so I replace as m lambda, then I have plus omega here. So, this omega I can replace as 2 pi c divided by lambda, there should be a plus sign, and now I replace dn d omega as this value. So, it should be minus of lambda square divided by 2 pi c and dn d lambda. So, eventually this 2 pi c will going to cancel out, and lambda square one term will cancel out. So, finally, I have V g, which is a function of lambda now, that for different lambda I have different group velocity. It should be c divided by n as a function of lambda minus lambda dn d lambda. This is one form, and if I want to write this in the frequency, in terms of frequency, it is V g c, which is the velocity of light, divided by n of omega plus omega dn d omega. So, these two form I can have if n is a given, if the function n, the refractive index is given as a function of lambda or is given as a function of omega. Based on that, I can use the V g in this way. Well, after having the V g, in order to calculate dispersion, we need to find out what is the time lag actually, that we calculated in earlier classes. So, here also t tau, which is a time taken by a wave, the time taken by a wave to move a distance L can be calculated as simply L divided by V g. V g is a group velocity. Now, it should be simply L divided by c multiplied by n of lambda minus lambda dn d lambda. Okay. So far it is fine. Now, if the source is characterized by a spectral bandwidth say delta lambda, then each wavelength component rather will travel with a different V g, different group velocity. This results something called a temporal broadening. Of the pulse. So, what is the meaning of that? So, suppose I have a source, very sharp source. So, normally this is the way to write a sharp source. So, this is a very specific lambda, say lambda 0, and when it is passing through, then since there is no frequency component, extra frequency component is a very sharp source lambda 0. So, the time taken by this, so d n d lambda, there is no such d n d lambda, because only one lambda are there. So, I should not have any kind of dispersion for that, because this is a single wavelength. So, less dispersion. Now, instead of having one lambda, if I have a range of lambdas, a range of lambda means if I have a width, bandwidth, say delta lambda 0, that means not only one lambda, different lambdas are present here, say one lambda is here, another lambda is here, another lambda is here. So, there is a spectrum with different colors like that. So, when I have a spectrum and when it is propagating, so what happened that in temporal domain there is a broadening. So, I should have a broadening in time domain. This is broadening. So, there should be temporal broadening of the pulse, because different component now will going to travel at different group velocity, and when it is traveling with a different group velocity, so there will be a stretching of the pulse depending on the value of the dispersion coefficient, and we'll going to have a broadening. So, that is, so we here we have dispersion, more dispersion. Now, quickly we calculate the dispersion coefficient. So, how the broadening is given? The broadening is given by delta tau, because delta tau is a measurement of the broadening, that how these things will going to broaden, and one can write this delta tau as d dt d lambda delta lambda. So, delta lambda is a width, and because of that one can have different time, and this is basically the measure of the temporal broadening. So, if I know what is tau, because I calculated that, it is L divided by Vg, and expression is L divided by C multiplied by n lambda minus lambda d n d lambda. So, I want to make a derivative of this quantity first. So, if I do, I will simply have L by C, there is a n first, so d n d lambda minus d n d lambda minus lambda, the second term d2n d lambda square multiplied by delta lambda. This term will going to cancel out. So, eventually I have minus of L lambda divided by C d2n, which is a function of lambda, d lambda square multiplied by delta lambda. This is my delta tau, the measurement of the temporal broadening. Well, I can define something like del m, which is delta tau divided by delta lambda L, which is temporal broadening. This quantity is nothing but temporal broadening per unit change per unit length per unit change of wavelength. So, by definition this is the change of this is the temporal broadening happening per unit length 1 by L and per unit change of wavelength delta tau. So, this quantity we call the dispersion coefficient. Delta m is eventually minus of lambda divided by c. From this expression I can write d2 n d lambda square, and in unit it should be picosecond per kilometer nanometer. This is a very important parameter which we call the dispersion parameter. So, today we do not have much time to discuss more about this. So, in the next class we are going to discuss more about the dispersion coefficient and how one can calculate that, and another kind of dispersion coefficient also be defined. So, with this note I would like to conclude this class. Thank you for your attention.